The standard approach for this integral is to compute recursively. So what we're gonna do is we will say this integral as I of n, yeah, and we will get some recursive relations of I of n with I of, let's say, n minus one, and then using that recursive relation we will get down to some base integrals like I of 0, I of 1, and then compute those integrals and find I of n. So let's see how we do that. Now in this like one of the approaches can be to take the sum of I of n plus 1 and I of n minus 1 and take their average, because if we do this, here will be cos n plus 1x and cos n minus 1x, their sum, yeah, and their sum can be changed to product, which eventually get to the same form. So let's see how. So if I add these two, I basically will have integral from 0 to pi 1 minus cos n plus 1 x plus cos n minus 1 x by 2. Yeah, I have skipped a lot of steps over here. So basically since the denominator will be same, we will just be averaging the sum of numerators, and 1 and 1 will be 2, by 2 is again 1, and over here you can see that, yeah. And this thing over here, it's actually minus, if it's not visible, it's minus 1, yeah, dx. Okay, now after this we can change this to a product, yeah. Integral from 0 to pi 1 minus, this is 2 cos, their sum will be 2nx, and divided by 2 is just nx, and difference is 2x, divided by 2 is x, cos x by 2, yeah, by 1 minus cos x. Now I was telling you that after we take the summed product, we will get the initial expression, yeah. Let me show you how. Now after this what we can basically do is we can introduce the cos nx over here, yeah, because we need that to take the origin, make the original integral, yeah. And now here is minus cos nx cos x, yeah. Also introduce a plus cos nx, yeah, and that will like help us simplify this integral a lot. You will see that soon, yeah. Now after this step what we can do is we can write this as integral from 0 to pi of 1 minus cos nx by 1 minus cos x, and then over here if you take cos nx common, this is just 1 minus cos x, yeah. So basically you have plus integral from 0 to pi, if you take cos nx common, this is just 1 minus cos x, isn't it, by 1 minus cos x dx, yeah. And now this over here is just I of n, and this will just be sin x over n, and at pi and 0 but both the limits sin of n x is 0, so that's why it actually goes to 0. So this is I of n, our I of n minus 1 plus I of n plus 1 by 2, this is I of n, yeah. Now we have got this, and something I think I should address is basically at 0 this is 1 minus 1 by 1 minus 1, so this is in the form of 0 by 0, yeah. And so basically like though it may be 0 by 0 form at 0, but at 0 plus at a point really near to 0, like it's defined and it's finite, and it's finite, so that's why the integral at the lower value it's bounded at some finite values. So basically if you take this limit 1 minus cos nx by 1 minus x cos x, this will actually be this will be 2 sine square uh, nx by 2 and 2 sine square x by 2. Again, that will be 2 to cancels out, and n square x square by 4 by x square by 4. So that this is just n square. Yeah. So this limit is actually a finite number, and so the limit is actually bounded to the lower values. I mean, at the lower side, and so this limit is this integral is also finite. So, but that's really not needed to solve the problem. Okay, now you see that let's say if we have a sequence, let's say a of n plus 1, a of n plus 2, and let me write it a of n minus 1 over here. Okay, now if the sequence is in AMGM, not AMGM, if the sequence is in arithmetic progression, in that case the a of n will just be the average of the other two. Yeah, and this is only if and only if the sequence is in arithmetic progression. The reverse also holds. Yeah, if this is holding, the sequence is in arithmetic progression, we can say that. That's why this sequence is these IFN sequence are also in arithmetic progressions. So that's why we can say that if we have to find I of n, like yeah, in that case what we can say is, let's say we have I of 0 and I of 1 with us. Yeah, the first two terms, because here are 3 variables involved, and then a plus n minus 1 d is the formula. Yeah, if I of 0 is the a, this is actually n plus 1th term, so n plus 1 minus 1, and d is I of 1 minus I of 0. Yeah, that's why we have I of 0 plus n times I of 1 minus I of 0. So we have n times I of 1 minus n minus 1 times I of 0 as I of n. Yeah, this is the okay, this is the point, this is the way for us to the answer. Now we need to find I of 1 and I of 0. Yeah, okay, so that is not too hard to find I of 1 and I of 0. I of 1 is actually integral from 0 to pi of 1 minus cos x by 1 minus cos x dx, and this is just 1, cancels out, integral from 0 to pi of 1 dx, and this is just x from 0 to pi, that's just pi. Yeah, and now I of 0 is integral from 0 to pi 1 minus cos, if n is 0, this is also 0, by 1 minus cos x. Now cos 0 is 1 and 1 minus 1 is 0. So integral from 0 to pi of 0 dx, integral of 0 is c from 0 to pi, that is c minus c, which is 0. Yeah, so we have I of 1 and I of 0 now. I of 1 is pi and I of 0 is 0. So using this, we have I of n is equals to n times pi minus n minus 1 times 0. So I of n is actually n pi. This was a pretty nice answer. Yeah, so we have finally solved this problem. The answer is n pi. And to talk about the flow, if I try to calculate this, because that would again simplify to the original expression, and yeah, and this would also like involve recursion and like reduce this problem to finding some lower values. And yeah, after we got this recursive relation, it was just about finding I of 1 and I of 0 after identifying that they were in a arithmetic sequence, and we could find the nth term. And yeah, that solved the problem. So thanks for watching, hope you learned something new, and look forward to seeing you in the upcoming videos too.